Oh, cool. I'm fixed. Let's start. So, good morning. Thanks for coming this early in the morning. I'm Nicolas. Since I'm quite young, since my young age, I've noticed, and I still notice that just computers are getting faster. And when I actually get into using computer, which in my case would be, oops, no cursor, but anyway, would be around here. CPU frequency was basically how we compared our computer, because that's exactly what was exponentially growing. But yeah, okay, this is a very small set of data that I picked from Wikipedia, so it's probably not fully representative, so don't look at the numbers. It's just a couple of computers, but you can see that it's flattening out. It's not like increasing crazy. But if you look at another bug is statistics, but if you look at the MIPS, you can see that actually computers are still getting faster and faster. And yeah, thanks to the car count, you can run a lot more instruction per second if you have more CPU, and that's quite fast. But it's quite pointless to do all these operations if you can't read and write the data that you've been calculating, basically. And this is not a timeline. It's just a couple of, it's an ordered list of RAM technology that has been put there. But what is interesting about this graph is that you can see that the frequency of RAM is much lower than the frequency of the CPUs. But you can see that the transfer rate, though, has been progressing quite fast. But to me, computers today are still growing, are still getting faster, and it doesn't seem to match really those statistics. And the truth is because your RAM is not working the way that it would work. Like, it's not in order. So when you access the RAM, you don't just get a byte. You actually trigger something in the system. You trigger caches, you trigger asynchronous operation that get feed into the cache, and your CPU or device. So I'm going to use CPU and devices interchangeably in the presentation, because caches are not just for your CPU. Basically get filled with the memory into a local memory for the device, and that is faster to access. The key point of this is that it works by pulling or pushing memory in group that are surrounding each other. And this behavior can be predicted. And this predictability of the memory can be actually used to improve performance. And that's where I'm going. So let's see how the video data storage works. So a while ago, in your TVs, there has been a convention to basically update or render the cells or the phosphate thing. I don't know, I'm not in that type of engineering, but in a raster scan order, meaning that you would update your image from top left, rows by rows, until you get to the bottom. And that actually translated into how we turn those analog signal into digital. So we just use the same order. So every rows are contiguous to each other into memory. And in fact, that works quite well for whether it's video capture, raw data transmission, for display. That's about how we want to use it. And so the storage and memory and the way we actually use it matches. But with GPUs and codecs, this is not how we use the pixels. The codec especially uses the neighboring differences and comparison in order to compress. So it's unlikely to go very far on one line. It's going to use a little bit of the first line and the same little bit on the next line. And this actually forms rectangle that we usually call macro block or tiles. And this is what they access. So with modern RAM, if you were to access this standard raster image, but you want to only read so the red line is actually the order of bytes in memory. And if you actually want to read the purple tile, you would read the first pixel. Probably that the entire row of that tile will go into cache. So by the time you're done processing your pixel, you might have access to the next one very quickly. But then there's a lot of the next tiles that the first row of the next tiles is going to be pulled into cache. And you're not going to use it because you're going to read the next line. So you're kind of wasting memory operation. And it's not exactly efficient. There's a way to fix it. And one way to fix it is to change the format. To change not necessarily the format itself in the way that we organize each pixels, but the way we organize the bytes in the picture. So here comes a tiling format. So when we say we have a tiled format, it's not necessarily about the content that has tiles like when you do sprites in your video games. They're tiled because they're organized in a way that each row of the tiles are contiguous to each other. So when you read the first byte of your tile, you're usually pulling at least the entire tile into cache. And that makes all the following operation more efficient. The RAM can operate asynchronously to your device. Now, tiles can be square, rectangular. They can even be full height. You'll find that. There's some system where a tile is just a column, and that's as efficient as any other rectangles. Actually, it gives you the flexibility of choosing your tile height, and it has the same thing. But yeah, it can be also combined with any of the pixel format you can think of. So yeah, there's a lot of them. Now, tile is not the only thing that can be done to improve. In fact, on most of the ARM SoC, the RAM bandwidth, the RAM speed, is just not sufficient for those high 8K, 60 frames per second videos that people definitely want on their TV. I don't know for you, but I've never watched an 8K movie in my life. But yeah, but that's the goal. You know, that's the future. That's where we're aiming at. And yeah, when the bandwidth's not sufficient, you can actually use predictability to fix it up. So this is a very atypical frame. This is not what you will find in your video. I mean, if it was like this, you couldn't do anything. So this is just a random frame. And well, in fact, for every developer out there, that's the typical frame, of course. And this is actually very predictable. You can see that neighbor pixel kind of are close by. So you can see that this pink part has other pink around it, which you could use. So you could say, oh, instead of storing this is pink +1, maybe I can store the +1. So this type of very simplistic lossless compression can actually be implemented in your memory controller. So your device will do read and write operation through a controller, and while the data goes through the controller, it will be compressed and decompressed, so that it doesn't have to actually store the entire data. So it can do smaller reads or smaller write. Of course, like any lossless compression, the worst case is going to be worse than your original image. So you have to allocate a little bit more memory for the case where the memory controller will need actually to do more work. But most of the time, you will reduce about, I would say, by half the amount of reads and write. And in practice, we've been testing this on the Huntro G2 hardware. We've seen like a 3-time saver on the bandwidth. And that actually reflects in a linear way on the frame rate for codecs, especially codecs, because think of a codec of something that takes n images to produce one. You still need to read these images, and that's a lot of read and write. So in our case, we were getting 3-time speed, and we were still post-processing into linear memory at the end of the process. So only the reconstruction part and reading all the reference, yeah. So as I said, it doesn't save any storage. It's only save on the amount of reads and writes. So don't get full. Actually, there exist technologies. Hello. There exist technologies that can use lossless compression on the memory controller for extremely cheap devices. But I think in television and video, that doesn't make much sense. And yeah, you'll see FBC being used in many places. And you'll see AFBC, the ARM FBC, or AFBC, the mLogic FBC. That's the kind of acronym you'll see around. Now, how do we support this? How do we handle this? Because, as we said, it's a combination. I mean, it's explosion and combination of formats that you would handle. So typically, vendors would say, "Oh, this is too complicated. Let's abstract it." And they would have like the one surface abstraction, and whatever they needed for their hardware, they would hide it behind that surface. And that's what you find in APIs like GL, VK, VA, D3D. It usually does not interrupt at some point. So as long as your API supports everything, you're fine. But if there's one thing that is not part of your API, or that is a separate PCI card, as an example, it doesn't work very well. And actually, when you try to do that, well, you already seen that in Victor's presentation, but that's what you get. And it doesn't look very good. This is what Intel white tile look if you render it in raster, if you ignore the fact that it's tile. So, as we said, size of image is the same. It's really the memory layout that is different. The alignment is a bit different, but that is visible in the stride, so that's why you can actually render it. How do we fix that? Well, we started fixing that in GStreamer a while ago on ARM devices by adding tile format. And I'm not regretting that addition. Tile format has been very useful, especially in the software converter, because that's what allows us to actually do conformance testing on those codecs, because we can actually convert the output of the codecs to the reference format and then compare the MD5 of the reference format against conformance tests. And that's a big deal. That makes a lot of differences. But adding all these formats, especially the weirdo one like the NV12 8L128 and is 10-bit variant, which is probably the most interesting since the tiles are in bytes, and then you need to take the last byte of the row of the tile and combine it with the first byte of the row of the next tile. Yeah, that's this kind of format. So it's very painful to do in software. It's something made for hardware, really. And this is ARM. There's a very small set of format that we actually use on ARM. When it comes to GPUs, they can have hundreds, and I say hundreds, but it's actually thousands of combination, because they're tiler, they're compressor, they're parametric. You can decide what tile size you want. You can actually configure it. So this method of just adding new format infinitely, it's just not sustainable. And that's something that the digital right management people, the direct rendering manager people, so yeah, it's a very confusing acronym. So that's the subsystem in Linux where the display driver and the GPU driver lives. Actually, they come up with a solution where they say, okay, we're going to keep our format. We're going to save our life of adding format infinitely. And we're going to add a modifier. And you've already been introduced to that with Victor, but yeah, a good review is always good. So the modifier is 64-bit. The first 8-bit, the one on the left in the register, it represents the vendor ID. And then it's up to the vendor to decide what to do with the remaining 56 bits. So that's it. In DRM, formats are defined as 4cc, so it's a non-standard. So GStreamer has 4cc. Nobody uses it, but we do have some. And it has nothing to do with the DRM 4cc, and it has nothing to do with the V4L source CC. So just be aware. We decided to stick with DRM for CC even in the negotiation inside GStreamer for simplicity and to ease actually the debugging when we look at, let's say, your kernel traces, your Wayland traces, they will all show you the same format. Because especially the reverse of RGB component in the name, it can be very confusing. DRM modifiers. So they're usually displayed as 16 hexadecimal numbers. There's a special number, the linear. The number 0 means that it's a linear format. Usually, when it's linear, it's also something that you can map to your CPU and use. So it's an assumption that everybody makes. So usually they just don't expose a linear format if it's not mappable. And there's this special format, vendor 0, like so no vendor with full F, which is named invalid, but it actually means it's not supported. And this is basically the legacy support for implicit negotiation, which does not always work. An example is this one. So OX1 with number 1, that's the Intel's X style. So Intel was creator of this concept, and 1 is the Intel vendor ID. Let's go over the implementation of basically this. So as we said, in order to fix it, we decided to explicitly negotiate those formats. And for that, we needed to introduce basically those formats into the caps. So we decided to reuse the DMABuf caps feature, even though there was a bit of concern on backward compatibility, just because you need a DMABuf to actually carry these information. It goes with DMABuf with the fact that you have a file descriptor to describe your buffers for the sharing. So it would have been confusing to just create a new one. And in order to fix backward compatibility, we introduced a format field, a new format that is straight into libgst video that is called DMADRM. And by adding a format, it means that we eliminate all the legacy DMABuf drivers, plugins actually that would use it because they don't have that format. So they don't negotiate. They won't be compatible basically with the other. And it's straight into the template caps. So the autopluggers works very well into eliminating those combinations. The actual format is set in a field called DRM format. It's a 2-part format with the 4cc column and the modifier. And that's what it looks like in real. Of course, DRM format can be a list, and it can be intersected, and everything. Now, over the years, when it started, the modifier thing, it was mostly for Mesa. Mesa knows about the hardware. So you didn't have to tell what modifier was supported. You could code that into Mesa and life was good. But modifier is for sharing. And in order to carry that and not program the notion of what modifier is supported for each hardware, they needed a way to enumerate at least the best possible candidates for a modifier for the current context. So that's API that's been added to OpenGL, the API, Wayland, of course, the DRM subsystem. Have these API. Wayland goes a little further because Wayland compositors basically have a dynamic pipeline. So they may actually, your software may switch from one GPU to the other if you have dual display on dual GPU. And of course, the optimal modifier is certainly not the one of the neighbor GPU. So if you're sending data with a modifier for GPU 1, but you're rendering on GPU 2, what the compositor have to do is go see GPU 1, say, hey, turn that into something GPU 2 supports. And then you bring that buffer to GPU 2 and you can import it. So in some ways, even though that whole 0 copy and everything, it could be worse to actually use a modifier. So the DMABuf feedback is a new API. There's a work in progress by my colleague Colin on the subject, and it basically notifies you which DRM device is going to be used for render. It could be a GPU or a display, and it's going to give you the preferred and supported format and modifiers. So you can adapt your rendering, your pipeline. For a game, it's really easy because you can just switch on the fly. But if it's a codec that directly renders to the display, that can be a bit more challenging. And that's it. The caps in GStreamer, it's a fantastic system. It just fixes it for you. It just intersects all these massive amount of data and gives you something to use. We don't do ordering. We depend basically on the stack giving us best ordering, and the caps actually maintain an ordering that actually makes sense. And we cannot guarantee it's going to be always the optimal thing to do, but it's definitely better than just always using linear. If you want to learn more about these things, we've written, I'll be uploading that right after the presentation to the website. And we've written a design document that explains basically why and how we added that into GStreamer. So there's a link for that. You may want to read the GST Video Info DMA DRM helpers. So it's a wrapper around video info that helps you parse the caps, of course, but it also helps you interrupt with the GST Video Info for the case where it's linear. You may want to read the DMABuf allocator API, if it's only to understand that it does not allocate memory. It only wraps memory into GST memory. It wraps FDs into a GST memory object. And there's also a nice summary on Victor's blog about all this work. I really need to thank Hee Jun Yang, who's not here, because he's the one who wrote basically everything. So we worked with him on the design. We did all the code review and suggestion. And there has been a lot of iteration of this. And yeah, he never gave up. And a full year of work, and we finally managed to merge it. I'd like to thank Collabora also for being here and letting me present today. So hope you enjoy. We have a good 8 minutes of questions. So.
Yeah, hello. I guess V4L2 doesn't support these modifiers, right?
Correct. So in V4L2, if we speak about the Linux kernel, they're still on a legacy format system. So for now, vendors have to add format in order to support tiling and compression. But the reality is that they're also adding compression. And this is not something we can add into GST video. So I would expect that in the next year, we start implementing the DMABuf features on top of that, and we'll just make a translation table so that when we have a tiling format, instead of using it as is, we're going to translate it to a DRM format and a modifier. So that would be it. There has been discussion in the Linux media community, but there's not much traction yet. So we hoped that Linaro, the Qualcomm team, was going to do something because they had to integrate the Qualcomm compression, the QC80 and QC something. But yeah, they ended up integrating QC80 and QC something straight as a format. Another hardware that entirely depends on that is Amlogic codecs in 10-bit. They only work if you use compression. That gives you an idea of the speed of the RAM. And yeah, we have some codecs where the compression is not very useful outside of it. So that's the case for upcoming Wave 5 driver. So there's compression, but it's not something that the other hardware. So you actually use compression internally for reference. So it's going to be RFBC. That's a very common acronym. But you produce linear image as a post-processing. Same for the Hantro G2. That's most likely what we're going to do. But the G2 actually on IMX8M, you can put that into the display, but not the GPU. So it's very inconvenient for a compositor, because if your compositor commits to rendering that and then you switch to a different display, you're screwed. You can't display anymore. So it's a challenge. some hardware is trying.
Is the hope that this will eventually replace something like NVMe memory? So instead of having these vendor-specific DRM things, then we'll just have this standard DRM for every hardware?
It's entirely dependent on NVIDIA in this case, because we're speaking about NVMe, which is something available in their BSP. NVMe is quite identical, so it's a little C structure that wraps most likely a DMABuf for Tegra platform and a view on Windows or something. So it wraps the actual representation of memory. It saves the width, the height, the stride, and the compression. So yes, it could, but be known that, I mean, in upstream discussion on the DRM side, they were not like the welcoming people around the DRM modifier stuff. So maybe not, they might change. But there's other companies like AMD that said that they would never do that. And today it's quite well supported. So ideas changes over time, over decades. I think that's it. Anyway, if any of you have more questions later, I'll be around. Just come by. I'll have my badge so you can recognize me. Oh, there it is. And yeah, hope you enjoyed this presentation and enjoy the conference. Thank you.